Pick any whole number you like, and try to build it by adding up square numbers, the ones you get by multiplying a number by itself. 1, 4, 9, 16, and so on. Some are easy. 2 is 1 plus 1, 3 is 1 plus 1 plus 1. But watch how few squares you ever seem to need. 7 is 4 plus 1 plus 1 plus 1, 4 squares. 15 is 9 plus 4 plus 1 plus 1, again 4. Try as hard as you like, and you will never be forced to use a fifth. Every single positive whole number, all the way up, can be written as at most 4 squares added together. That is a real theorem, proved by Joseph Louis Lagrange in 1770, and it is the seed of our whole story. So the expression made of 4 squares, the first square plus the second plus the third plus the fourth, with each allowed to be 0, is a kind of machine. Feed it the right inputs, and it can output any positive integer at all. Nothing gets left out. A machine that reaches every number is called universal. And the question that will run away with us is deceptively simple. How could you ever be sure a machine like that truly misses nothing? 4 squares is not the only such machine. It is one of a whole family. You are allowed to weight the squares. Instead of the plain sum, you could take 1 of the first square, plus 2 of the second, plus 5 of the third, plus 5 of the fourth. That is a different machine, a different sum of squares recipe, and mathematicians call these recipes quadratic forms. Change the weights, and you change what the machine can build. Some of these weighted machines are still universal, reaching every positive integer, and some are not, forever missing certain values no matter what you feed in. Back in 1916, the Indian mathematician Ramanujan wrote down a famous list of the weighted 4 square machines that are universal. There are 54 of them, and not one more. To feel the difference, our earlier machine with weights 1, 2, 5, and 5 looks perfectly reasonable, and it does reach an enormous run of numbers. But it is not universal. There are values it can never build, and you would have no way of guessing that just by trying the first handful. The plain 4 square machine, by contrast, reaches everything. From the outside, the two look almost alike. That is the trap. Universality is not something you can eyeball, so universality is special, but it is not rare. Plenty of these machines reach everything, which sharpens the real problem. Suppose someone hands you a brand new weighted machine and claims it is universal, that it can produce every positive integer without exception. How on earth do you check a claim about every integer when there are infinitely many of them to test? Sit with how hopeless that verification sounds at first. To be certain a machine reaches every positive integer, the naive plan is to try them one at a time. Show it can make 1, then 2, then 3, and 4, and on forever, never finishing, because the whole numbers never run out. Even if you checked a trillion of them, and every single one worked, that would prove nothing about the trillion and first. A machine could sail through billions of values and then quietly fail at some enormous number far past anywhere you looked. Verifying a property of all integers by brute force is exactly the kind of task that has no end. And yet, for these sum of squares machines, the situation turns out to be the complete opposite of hopeless. You do not need to check infinitely many numbers. You do not even need to check 100. There is a tiny, fixed shopping list of integers, the same list for every machine. And if your machine can produce just those, it is guaranteed to produce all the rest. The infinite check collapses to a finite one. That is the result we are here for. Here is the shopping list. There are only 9 numbers on it. 1, 2, 3, 5, 6, 7, 10, 14, and 15. That is the entire list. The theorem says this: take any of these weighted sum of squares machines with whole number weights. If it can produce all 9 of those numbers, then it can produce every positive integer there is, with no exceptions, all the way to infinity. If it fails even one of the 9, it is not universal. 9 little checks decide the whole infinite question. This is the 15 theorem, and it was proved by John Conway and William Schneeberger in 1993. Look at what a strange and powerful statement that is. It reduces a question about an infinite set of integers, which sounded genuinely unanswerable a moment ago, to 9 arithmetic checks you could do by hand over lunch. The name comes from the largest number on the list, 15. And notice which numbers are absent. There is no 4, no 8, no 9. Only these 9 oddly chosen values carry the entire weight of the theorem. Why exactly these, and why 15 at the top, is where the real beauty lives. Let us actually run the test on our first machine, the plain sum of 4 squares. We go down the list and represent each of the 9. 1 is just 1 squared, 2 is 1 plus 1, 3 is 1 plus 1 plus 1, 5 is 4 plus 1, 6 is 4 plus 1 plus 1, 7 is 4 plus 1 plus 1 plus 1, 10 is 9 plus 1, 14 is 9 plus 4 plus 1, and 15 is 9 plus 4 plus 1 plus 1, 9 for 9. Every number on the shopping list is reachable, so by the theorem, the 4-square machine represents every positive integer, exactly as Lagrange proved the long way in 1770. We just reproved a 250-year-old theorem with 9 lines of arithmetic. That is the theorem as a tool. Hand it any machine, run 9 checks, and you know its entire infinite behavior. But a good result should not just be a tool you trust blindly. It should have a reason. And the reason behind the 9 numbers is a beautiful little idea about the smallest thing a machine cannot yet do. To see where the 9 come from, start not with a finished machine, but with an empty one, and build it up. Give yourself a single square to work with. On its own, it represents 1, 4, 9, and the other perfect squares. But the smallest number it simply cannot make is 2. Call that smallest unreachable number the truant, the first integer playing hooky. To fix it, add a second weighted square chosen to capture the truant, and now you can make 2. But your patched machine has a new smallest failure. With 1 square and a double of another, the smallest number you cannot reach is 5, so 5 becomes the next truant. Patch that, and the new truant jumps to some larger value. Every time you plug the smallest hole, a new smallest hole appears a little further out. You can watch it happen concretely. 1 square alone stumbles first at 2. Add a plain second square, and the smallest hole moves to 3. A single square with a doubled one fails first at 5. 3 plain squares get you all the way to 6 before stumbling, and their first miss is 7, the famous fact that 7 is the smallest number, not a sum of 3 squares. Every one of those first failures is a number we will meet again, and here is the quietly astonishing part. The truants that show up in this patching process are never random. They are always drawn from the very same short list: 2, 3, 5, 6, 7, 10, 14, 15. The smallest failure of a sum of squares machine, whatever machine you build, is always one of those special numbers. The 9 are not chosen by hand. They are forced, as the only places these machines are ever allowed to stumble. That patching idea is the whole engine of the proof, and it has a name: escalation. You start from empty, and you keep adding squares, each one chosen to defeat the current truant, the current smallest failure. What Bhargava showed, giving a beautifully clean proof of the theorem years after Conway, is that this process always ends fast. No matter how you make your choices, after at most 4 squares the machine has no truant left at all. It reaches everything. There is simply nowhere left to fail. And because every step is governed by that same short list of possible truants, the entire infinite question is corralled into a finite tree of cases, each one settled by hand. So the deep reason 9 checks suffice is this: a universal machine is one with no truant. A non-universal machine has a smallest failure, and that failure is always one of the 9. Therefore, any machine that clears all 9 has no possible place left to fail, and must be universal. The finiteness was hiding in the truants the whole time, which finally lets us answer the question in the title: why does the list stop exactly at 15? 15 earns the top of the list by being the hardest single test, and there is a specific machine that proves it. Consider the weighted machine that takes 1 of the first square, 2 of the second, 5 of the third, and 5 of the fourth. Run it down the shopping list. It makes 1, 2, 3, 5, 6, 7, 10, and 14 without any trouble. 8 of the 9. It sails through everything on the list, right up until the last entry, and at 15, it stops. There is genuinely no way to build 15 out of those particular weighted squares. Its truant is exactly 15, and nothing smaller. This is why 15 cannot be dropped from the list. If the shopping list stopped at 14, this machine would pass every check, and be wrongly declared universal, even though it can never make the number 15, or, it turns out, infinitely many numbers beyond it. 15 is the single value that catches this last, most stubborn imposter. It is the final gate, the hardest thing a non-universal machine can still sneak past if you are not watching. That is what puts it at the top of the list, and what gives the theorem its name. There is a second act to this story, and it is even grander. The 15 theorem covers machines whose weights are whole numbers. But there is a slightly larger world of sum of squares machines. Ones allowed a few half-integer ingredients, and for those, the 9 numbers are not quite enough. In 2005, Bhargava and Jonathan Hanke proved the natural sequel. For that bigger world, there is again a finite shopping list that decides universality completely, and it also stops at a single largest number. This time the list has 29 entries, and the number at the top is 290. Check those 29, and once more you have certified an infinite claim. So the miracle is not a one-off accident of the number 15, it is a genuine phenomenon. These sum of squares machines, for all their infinite reach, are pinned down by a finite set of critical values, a handful of numbers that hold the whole structure in place. 15 governs one world, 290 governs the next. In both, an infinite truth is decided by a short, checkable list. Step back, and the shape of the thing is genuinely surprising. We started with a question that looked unanswerable. Does this machine reach every one of infinitely many integers? The brute force answer never ends, and the resolution was not a faster way to check infinitely many numbers. It was the discovery that you never had to. The whole infinite behavior of a sum of squares machine is decided by whether it clears 9 specific hurdles. 1, 2, 3, 5, 6, 7, 10, 14, and 15. Clear them, and you have reached everything, forever. The real lesson is bigger than sums of squares. Again and again in mathematics, an infinite question turns out to have a finite heart, a small set of critical cases that secretly control everything. Find that set, and the impossible becomes a checklist. Conway and Schneeberger found it for the whole number machines, at 15. Bhargava and Hanke found it for the next world, at 290. And each time, the endless was quietly settled by the finite. If there is one thing to carry away, it is that certainty about the infinite can hide inside a list you could write on your hand. This was another one in the series. Stay for the next.